Hello, my dear students. Welcome back to the online lecture video series on electromagnetic theory by AVS Deepak. In the previous module, we have seen what are the various types of vector fields and how to represent the time harmonic vector field using its phasor representation. Then we have analyzed the relationship between phasors of a field and its time differentiation, and then we have discussed the relation between phasors of a field and its time integration. After analyzing the relations, we have derived the Maxwell's equation for time harmonic fields in the phasor form. We have discussed that the importance of phasor form is that it removes the time variation. Phasor form is only phase dependent. It does not vary with time. It varies only with space. So if somebody has given you phasor of some quantity and has asked you to determine its corresponding time variant version, then all you have to do is multiply it with exponential of j omega t and take the real part of it. That would give you the time domain expression for any quantity. So this is the relationship between phasor and a time domain expression. And the advantage of that phasor form is that we no longer have to worry about its time variation. We just have to analyze with respect to space. In the current module, we would discuss waves and parameters of wave propagation. The contents of today's module are, we would discuss waves and then we would discuss the wave propagation parameters. The wave propagation parameters we discuss are wavelength, time period, frequency, and wave propagation velocity. After I discuss these four, I would try to establish the relation among these four. Then we would discuss angular frequency, attenuation constant, phase constant. And then we would discuss the wave equation in phasor form. While discussing waves, we would start with a wave equation which is in time and space domain. Then I would discuss a wave equation which is just in space domain. That is an equation of a wave independent of time. After discussing these wave propagation parameters, I would discuss the electromagnetic wave and its propagating characteristics. What are waves? Waves are means of transfer of energy. The best example I can think of is an acoustic wave. In other words, a sound wave. Now, if I am the person who is speaking here, and you are the person who are listening, you have one more friend of you who is just a far away from you, a bit far away from you. When I speak, I produce energy, and those energy create vibrations and thereby the transfer of acoustic wave, as you all know. Now, when it is traveling in this direction, you would be experiencing some energy. That energy which you have experienced is the transfer of energy from the source to destination. You are destination 1 and your friend is destination 2. The intensity you experience at time equals to 5 is different from the intensity you would experience at time t equals to 10. At the same time, the intensity your friend experienced at time t equals to 5 is not same as the intensity you have experienced at time t equals to 5. And not just that, the intensity he'd experience at t equals to 10 is also not same as the intensity he would experience at time t equals to 10. In fact, it is also not same for you. Similarly, the intensity he has experienced at time t equals to 10 is not same as the intensity you would experience at time t equals to 10. That is, same person that at same location experiences two different intensities at two different instants. Similarly, at the same instant, two persons at different locations experience different intensities. Thereby, they say a wave is a function of time and space. Here, I am writing just one variable, but it can be of multiple variables x, comma, y, comma, z, depending upon the dimensionality of the problem. But for our initial discussion, let us just keep one dimensional problem, therefore only one variable to represent space. If somebody has asked you to write sinusoidal signal, you would be writing sine 2 pi f3t. And if somebody has asked you to write an exponential decaying signal, you would be writing exponential of minus t tau. The common factor in those terms is both the signals are function of time. Not just these two, any signal you can think of is a function of time. Whereas a wave is a function of time and space. That means this wave is going to vary with respect to time and also with respect to space. But the time variations and space variation of a wave are not independent. They are related to each other, and they are related with an equation called as wave equation, given as the first term in this expression corresponds to the time variation in the scalar quantity S. We are talking about a scalar wave. That means S is a scalar quantity. And this is the space variation. That is, it is varying with respect to x. This is time variation and this is space variation. These two are related with a variable u, which is called as the propagation velocity. This is the velocity with which the wave is traveling. If I solve this differential equation, I would be getting wave to be a function of x minus ut or x plus ut. It would be a function of x minus ut if the wave is traveling along positive x-axis, and if it would be a function of x plus ut if the wave is traveling along negative x-axis. This is a function of x minus ut and this is a function of x plus ut. Both the functions are independent of each other. So earlier when I said that the wave is a function of x comma t, now it has been modified that it is not a function of x comma t, it is in fact a function of x plus or minus ut depending upon the direction in which the wave is traveling. To illustrate even further about this wave and its time variation and space variation, let me show you an illustration which I have imported from the reference which I have provided at the end of this presentation. This is the source x equals to 0. This is a point x equals to 10.25 units of distance. That is, the red dot is at a distance of x equals to 10.25. I have two graphs, graph 1 and graph 2. The first graph, I am recording the instantaneous variations of red dot. That is the first graph, that is the instantaneous variations of the red dot. Whereas the graph 2 is a screen capture, a capture of the plane at time equals to 27 seconds. Let us start with the animation. See, till now, red dot has not received any energy or any intensity. Therefore, it was lying dormant. But as soon as it receives some input, it starts going up and down. And by this time, the variations have gone to zero, and after that, even for some time, it is again lying dormant. And here I have captured at time t equals to 27 seconds. Let me illustrate the importance of these two graphs. The first graph, I would try to illustrate why wave is a function of time. As I have told you that the graph 1 is recording the instantaneous variations of the red dot, right? Till 10th second, there was no variation and it was lying at 0. But after that, it has gone up and down, up and down, up and down. At 20th second, this is the intensity value as seen by the red dot, and time 30 seconds, this is the intensity value. Right? So at different time instants, the same point is experiencing different values of intensity. Therefore, a wave is a function of time. If a wave is not a function of time, if it is just a function of space, then for every time it would be receiving the same value, but it is not the scenario. It is experiencing different intensities at different time instants. Therefore, wave is a function of time. Similarly, in the second graph, which I have captured at time t equals to 27 seconds, I have plotted the amplitude versus position. This is the position. As I have told you, this is x equals to 0 and this is x equals to 10.25, and like that, this is x equals to 30. That is the end. So in this graph, I can see that at x equals to 0, the variations have gone down. They are 0. There are no variations. But at the distance x equals to 5, this is the intensity present. And at the distance x equals to 10, this is the intensity present. And at distance x equals to 15, this is the intensity. And x equals to 20 is this, and then x equals to 25. At same time instant, different positions are experiencing different intensities. Therefore, I can say that wave is also a function of. You can also see that the functions are pretty similar except for the scaling factor. That is, it is defined, the same function is defined on both time and space. The only difference is a scaling factor here, u. Now that we have understood that a wave is a function of time and space, let us discuss how many types of wave propagation are present. There are two types of wave propagation. They are a lossless wave propagation, where the energy as perceived by points which are at different distances. For example, if this is the source, as you move in this direction, the distance from the source is going up. But even if the distance from the source is going up, you can see the envelope, that the peak points of the wave, they are in the same level. As you know that a sinusoidal signal has a power of AC square by 2, and if it is for limited duration, then the energy received by a sinusoidal signal is AC square by 2 times capital T, the time for which the sinusoidal signal is present. In AC square by 2 capital T, if AC is constant, then the energy received by every body is constant. As you can see, even though there are multiple points which are further from this source, all of them are receiving same EC, therefore all of them are receiving same energy. That means no energy is lost in propagation. Such type of wave propagation is called as lossless wave propagation. Now let us see lossy wave propagation. Lossy wave propagation looks like this. You may see that the peaks are following a curvature. They are not on same level. They are going down as the distance from the source is going up. That means the energy received at a point which is further from the source is less than the energy received by a point which is nearer to source. That means there is some loss of energy. Such loss is called as attenuation loss. In the earlier discussion of us in this module, we would just discuss a lossless wave propagation, but in the end, we would discuss a lossy wave propagation along with an attenuation constant. So let us discuss various wave propagation parameters. The first wave propagation parameter we will be discussing is wavelength. Wavelength is defined as the distance the wave has to travel before repeating itself. And this is for a lossless wave transmission. Because a lossless wave transmission sees the same ripple going. The size of the ripple is also maintained. But it is a lossy wave propagation, just the shape but the size is not retained. That is, the peaks may go down. In that case, instead of calling it repeating itself, I can say the distance wave has to travel to complete one cycle. When a wave completes one cycle, it undergoes a displacement of 2 pi radians. One complete cycle means an angular displacement of 2 pi radians. It is represented using lambda. Let me illustrate that graphically. This is the graph which I have plotted at time t equals 27 seconds. It shows the amplitude versus position. Now, if you consider this point, the phase at this point is 0 degrees or 0 radians. Whereas the phase at this point is pi by 2 radians. I am assuming a sinusoidal signal, so the phase there is pi by 2 radians. And the phase here is pi radians. Phase here is 3 pi by 2 radians. And the phase here is 2 pi radians, and the phase here is 5 pi by 2 radians. The distance between these two phases are 2 pi radians. You can see that a sinusoidal signal has completed one complete cycle. Therefore, the angular displacement is 2 pi radians. The distance between these 2 points is called wavelength lambda. In fact, not the distance between just these 2 points, it can also be the distance between these 2 points. Any point on a wave you consider and you undergo a complete cycle, that is an angular displacement of 2 pi radians, the distance between those 2 points is called one wavelength. The next wave propagation parameter we will be discussing is time period. It is defined as the time wave has to travel before repeating itself. In other words, it is the time taken to complete one cycle. Again, one cycle means an angular displacement of 2 pi radians. It is represented using capital T. So if this is the amplitude versus time plot, that is graph 1, the instantaneous variations, we have plotted at x equals to 10.25, and if we follow the same pattern, this phase is 0 radians, this is pi by 2 radians, this is 5 radians, this is 3 pi by 2 radians, this is 2 pi radians, and this is again 5 pi by 2 radians. So when a body has gone from here to here, it has undergone an angular displacement of 2 pi radians, and the time gap between these two points is called one time period, capital T. Again, not just these 2 points, you take any point and go an angular displacement of 2 pi radians, the time taken to reach this point from this point is called the time period capital T. The next wave propagation parameter we'll be discussing is frequency. Frequency is the number of times wave repeats itself in a unit time. This is again for a lossless wave transmission. For a general case, it is the number of cycles in unit time. Obviously, it is inversely related to the time period, because if one cycle takes 0.2 seconds to complete, then in 1 second, how many cycles are present? The answer would be 5, because it takes 5 cycles to complete 1 second. Similarly, if a body takes 0.5 seconds, then in 1 second it can complete 2 cycles. The relationship between the time period and frequency of a wave is f equals to 1 by capital T. The next wave propagation parameter we discuss is wave propagation velocity. Classic physics says the velocity is displacement by time traveled. So for wave propagation velocity, it is the distance traveled by a wave in unit time. It is generally represented as u. So if I have to establish the relationship between lambda, u, capital T and f, I consider a wave that has traveled a distance of wavelength lambda. If it has traveled a distance of wavelength lambda, that means it has completed 1 cycle. The time taken to complete 1 cycle is capital T. Then, according to the definition, the velocity is displacement by time period, therefore lambda by capital T. I can also write this to be equals to lambda times 1 by capital T, where 1 by T is the frequency f. Therefore, I can write this to be equal to lambda times f. U equals to lambda f. This is a very famous result we will be using most commonly. This is the wavelength lambda, and this is the time period capital T. The wave propagation velocity is lambda by capital T. The next wave propagation parameter we'll be discussing is angular frequency. Angular frequency is called as angular velocity. When I say angular velocity, it is pretty obvious that it is angular displacement experienced in unit time. Consider that a wave has traveled for a distance of 1 time period capital T. If it has traveled for 1 time period capital T, that means it has completed 1 cycle. 1 cycle means an angular displacement of 2 pi radians. Therefore, angular velocity is 2 pi by capital T. I can also write this to be equals to 2 pi times 1 by capital T, where 1 by capital T is f. Therefore, omega equals to 2 pi f. This is also a result which is very commonly used. Omega is called as the angular frequency. The next wave propagation parameter we'll be discussing is phase constant. The difference between phase constant and the angular frequency is angular frequency is angular displacement per unit time, whereas phase constant is the angular displacement per unit distance. So consider that a wave has traveled a wavelength lambda. If it has traveled for a distance of wavelength lambda, that means it has completed a 1 cycle. That means an angular displacement of 2 pi radians. So the angular displacement per unit distance is 2 pi by capital lambda. If I multiply both numerator and denominator with frequency f, I can rewrite this expression beta to be equals to 2 pi f by lambda f, where 2 pi f by lambda f, 2 pi f can be written as omega as we have seen just now, and lambda f is the wave propagation velocity u. Therefore, beta can also be written as omega by u, that is angular frequency by wave propagation velocity. This is also very common result which we will be using. The next wave propagation parameter we will be discussing is attenuation constant. The difference from the attenuation constant to all the other constants which we discussed till now is all other constants, all other wave propagation parameters exist for all the wave propagations, but the attenuation constant exists only for lossy propagation. It does not exist for a lossless wave propagation. It is a medium specific quantity, as are so many other parameters we have discussed, and it gives us the amount of attenuation a wave experiences when it travels a unit distance in the medium. That is, if a body has traveled a unit distance, for example, see, the intensity here is not same as the intensity here, because a wave has got attenuated. Now, if for 2 units of distance, this is the attenuation received. If it travels for 1 more unit, what would be the attenuation which would be experienced? The attenuation constant generally characterizes this exponential curve. It is represented using alpha, and its value we would discuss in the next slides. This is the wave equation which we have seen in our first slide. This is relating time variations of a scalar wave to space variations of the same. But if we assume that the scalar wave which we are discussing is time harmonic in nature, then I can remove the time variations using its phasor form. So if I do that, I can transform this differential equation. But to transform this differential equation, I would recollect the relationship between phasor of a field and its time differentiated version. If the phasor of the scalar quantity S is Sp, then the phasor of its time differentiation version S dash is Sp j omega. Now Sp j omega is the phasor of S dash. Now what is the phasor of double dash is Sp j omega times j omega. So if I use this expression to convert this wave equation into its phasor form, I would get that j omega whole square times Sp minus u square times dou square Sp by dou x square is equal to 0. Understand that I have just removed the time variations, the space variations are kept intact. Because as you know, phasor is space variant. From the principles of complex numbers, j square is minus 1 and there is a minus already here. So I can rewrite this expression to be omega square Sp plus u square dou square Sp by dou x square is equals to 0. If I divide this right hand side and left hand side with u square in fact, then I would be getting that dou square Sp by dou x square plus omega by u whole square Sp is equals to 0, where we have just seen that omega by u is the phase constant beta. So I can rewrite this expression to be dou square Sp by dou x square plus beta square Sp is equals to 0. This is a partial differentiation in just one variable. Consider these two equations. These two equations are discussing the same parameter. In fact, this is discussing a time variant version and this is discussing a phasor version. But out of them, it is looking complex to solve because it is differential equation with two variables, whereas This is differential equation with just one variable and it is very easily solved. That is the advantage I can get by using the phasor representation of time harmonic quantities. So if I solve this differential equation, the solutions I would be getting would be of the form a cos plus or minus beta x, b sin plus or minus beta x, and c exponential of plus or minus j beta x. These are the possible solutions for the phasor of SP. Now, if I get SP, for example, say this is the SP I got, this is the phasor version I got, then the time domain version S of t comma x would be equal to real part of c times exponential of plus or minus j beta x, depending upon the direction in which the wave is traveling, times exponential of j omega t. As you know, this is how you get a time domain expression from a phasor form. Then that is equal to, if c is assumed to be a real number, this is c times real part of exponential of j omega t plus or minus beta x. Though exponential of j omega t plus or minus beta x can be written as cos omega t plus or minus beta x plus j sin omega t plus or minus beta x. So the real part would be c times cos omega t plus or minus beta x. So this is the time domain version I would be getting from this phasor form. Similarly, if this is the phasor form, then I would be getting, let us analyze that too. If the phasor form I have considered is a cos, for example, let us just consider beta x, then the time domain version S of t comma x would be equals to real part of a cos beta x times exponential of j omega t, where exponential of j omega t is cos omega t plus j sin omega t. So it is a times real part of cos beta x times, let me say, cos omega t plus j sin omega t. When I multiply this, this is the complex part and this is the real part. So I would be getting a times cos beta x cos omega t. So this can be rewritten as a by 2 cos omega t plus beta x plus a by 2 times cos omega t minus beta x. This is the time domain expression if the phasor is of the form a cos beta x. Similarly, if it is a sin beta x, then I would be getting, instead of cos here. So this is how I can get a time domain expression from solving just the space variant phasor differential equation. Let us consider an example that S is equals to a cos omega t minus beta x. In this, a is the amplitude and omega t minus beta x is the instantaneous space that is varying with respect to the time and also the space. Static fields won't travel. That is, if you have a static electric field, then it would be the static electric field for any time. It is just going to vary with respect to space, but it is not going to move from one point to another point. As seen in Maxwell's equation, time varying magnetic fields create space varying electric fields. That is, if a magnetic field is varying with time, it is resulting in a space varying electric field. The meaning of curl is its space variation. Time varying electric field is creating a space varying magnetic field. These continue to exist until the energy is absorbed by the medium in which these fields are propagating. If the medium does not absorb any energy, these continue to propagate for any longer distance. That is how electromagnetic waves are created, and that is the principle behind the working of your antennas. So how does antennas work? You have an antenna. If current is flowing through this antenna, then it creates a magnetic field around it, as we have already seen in magnetostatics, right? But if the current flowing through the antenna is not constant, instead it is time varying, then the magnetic field which is being generated would also be time varying. If the magnetic field which is generated is time varying, then it creates a space varying electric field. Now, because of this space varying electric field, whose intensity is not going to be constant with respect to time, this would be a time varying also. Because this is time varying, now this time varying electric field produces a space varying magnetic field. And the space varying magnetic field is also going to be time varying, and it is going to produce a space varying electric field, and these continue to propagate until and unless all the energy inside these fields has been removed, as this conduction losses J is sigma E. Sigma is the conductivity of the medium. If this conductivity is low, that means these waves are going to travel for a longer distance, and if this conductivity is high, then these waves are not going to travel for longer distances. This results in a loss. So until and unless the energy between them is lost, they continue to propagate. This is our electromagnetic wave propagation and the principle behind it. So let us see what are the propagation characteristics of an electromagnetic wave. So from Maxwell's equations, I can write del dot dp is equals to rho vp, where these two are representing the phasor representation, and del cross ep bar is equals to minus j omega bp bar. But if I write bp to be equals to mu times hp bar, I can write this also to be equals to minus j omega mu hp bar. Del dot b bar is going to be 0 even in the phasor form. Del dot bp bar is equals to 0. But interestingly, del cross h bar, which was equals to j bar plus dou d bar by dou t, when it is in phasor form, this del cross hp bar is equals to jp bar plus j omega dp bar. But this jp bar can also be written as sigma ep bar, and this dp bar can be written as epsilon ep bar. Therefore, del cross hp bar is written as sigma plus j omega epsilon times ep bar. Now, these two are purely in terms of electric field intensity and magnetic field intensity. And let us see how they work. I know that del cross ep bar is equals to minus j omega bp bar, and I can also write this to be equals to minus j omega mu hp bar. Taking curl on both sides of equation 2, I can write this to be del cross ep bar is equals to minus j omega mu times del cross hp bar. But del cross hp bar is equals to, as we have seen earlier, sigma ep bar plus j omega epsilon ep bar. So if I write this, that is equals to minus j omega mu times sigma plus j omega epsilon ep bar. From the vector identity, that del square of a bar is equals to the gradient of its divergence minus curl of its curl. So I can write the curl of curl to be gradient of divergence minus the Laplacian. If we assume a charge free region, that means the divergence of EP bar, which is equals to rho b p by epsilon, If I have assumed a charge-free region, then the divergence of EP bar is going to be 0. Therefore, its gradient would also be equals to 0. I get an expression that Laplacian of EP bar is equals to j omega mu times sigma plus j omega epsilon times EP bar. Bring them both onto one side, I can write del square EP bar minus j omega mu times sigma plus j omega epsilon times EP bar is equal to 0. This is of the form del square EP bar minus gamma square EP bar is equals to 0. This is the vector form of wave equation we have seen. We have seen the scalar wave equation. This is the vector form of wave equation where gamma is called as the propagation constant. This gamma comprises two factors alpha plus j beta, where alpha is the attenuation constant and beta is the phase constant. If I have gamma a complex number to be equal to alpha plus j beta, then the magnitude of gamma is root over alpha square plus beta square. If I square gamma, then I get gamma square to be equals to alpha square minus beta square plus 2j alpha beta. And if I try to determine the magnitude of this gamma square, this is equals to alpha square minus beta square plus 2 alpha beta whole square. And these are under root. This would give me alpha to the power of 4 plus beta to the power of 4 minus 2 alpha square beta square plus 4 alpha square beta square under root. That would give me, if I cancel them, I can cancel them like this, because this is 4 alpha square beta square, this is minus 2 alpha square beta square. The result is plus 2 alpha square beta square. Therefore, this is equals to root over of alpha square plus beta square whole square. So the magnitude of gamma square is alpha square plus beta square, which is the square of mod gamma, because mod gamma is root of alpha square plus beta square. This is what we have obtained. Now, what is the real part of gamma square? The real part of gamma square is alpha square minus beta square. And modulus of gamma square is equals to alpha square plus beta square. If I add these two, real part of gamma square plus mod gamma square would give me 2 alpha square. Therefore, alpha square would be equals to 1 by 2 times of real part of gamma square plus mod gamma square. Now, alpha is equals to root over 1 by 2 real part of gamma square plus mod gamma square. Beta is going to be root over 1 by 2 times mod gamma square minus real part of gamma square. So this is the relationship between alpha and beta to mod of gamma square and real part of gamma square. So if we go back to the values of gamma square I had, gamma square is equals to j omega mu sigma plus j omega epsilon. I can rewrite this to be equals to j omega mu times sigma plus j square omega square mu epsilon, whereas j square is minus 1, so this would be converted into minus omega square mu epsilon plus j times omega mu sigma. So the real part of gamma square is minus omega square mu epsilon. If I take omega square epsilon square common out of this, I can get this to be equal to omega square mu epsilon times root over sigma by omega epsilon whole square plus 1. So the magnitude of gamma square is this. From this, I can attain the values of alpha and beta in such manner. So these are the wave propagation parameters alpha and beta for an electromagnetic wave. These are the references. This is where I have downloaded the illustration of a wave, a GIF image, and this is where I have got the image for lossless wave propagation and a lossy wave propagation. And for elements of electromagnetics by Matthew Siddiqui for our general discussion. Thank you for attention. Meet you in the next module.